Hello, we are Michigan Tech Biomedical Engineering Department, Senior Design Team 13. Our project is Phase 5 Transcatheter Single Ventricle Device. I'm Kelsey LeMay, and I'm here with Gabrielle Lorenz and David Atkin. Hypoplastic left heart syndrome is a congenital heart defect that results in an underdeveloped left ventricle, which prevents the infant's heart from providing optimal oxygenated blood to the infant's body. And HLHS impacts 1 out of every 4,344 infants in the US. Our senior design team was tasked with prototyping and testing a transcatheter single ventricle device to replace the current HLHS stage 1 palliation surgery. Our stent device will keep the ductus arteriosus, or DA, pen for 3 to 6 months and will equalize the flow between the pulmonary arteries, or PA, and systemic circulation with the use of our fenestrations. We also created a repeatable benchtop model to mimic the infant blood circulation in order to test our stent device. Our benchtop model for testing our stent device models the HLHS preoperative conditions, and the model is robust and allows for repeatable tests to collect reliable data to show that our stent device equalizes the flow between the PA and systemic circulations with the use of fenestrations.
Image of the benchtop model Team 13 designed. The reservoir to the left represents blood volume. The peristaltic pump and Windkessel flask mimic the heart's pumping function. The 3D printed infant heart helps model relevant flow conditions, which is zoomed in on the right. The flow from the 3D heart will go through 2 outputs. One output represents the pulmonary artery that has a clamped in fenestration, also zoomed in picture on the right, that reduces flow going to the compliance box, which represents lung conditions by reducing the pressure using the vacuum pump. Lastly, the second output represents the systemic flow through the ductus arteriosus. The left was used to determine what pressure was needed for a 1/5 resistance. Using the pressure of negative 101.6 millimeters of mercury, calculated from the previous equation, a QP-QS ratio of 4.43 was determined. This closely matches the preoperative QP-QS ratio of 4:1 of the Aplasia HLHS model.
Benchtop modeling was performed over the course of 3.5 minutes using a flow rate of 130 milliliters per minute. 5 trials were performed for each fenestration size in each sample. The fenestration sizes were 0.35, 0.5, 0.75, 1, and 3 respectively. The dotted lines represent each sample's relative trend, and the overall line is represented by the green solid line. Its equation is indicated up here, and the optimal fenestration after solving this equation is 0.6 millimeters to obtain the 1-to-1 pulmonary to systemic flow ratio. In Aplasia, modeling this same 1-to-1 systemic to pulmonary ratio gave a 2.5 millimeter fenestration size as the optimal size for these conditions. In order to better have our setup model the HLHS physiological conditions seen clinically, we need our physical setup to have a better viscosity to match using blood mimic fluid, a flow rate that is closer to physiologically relevant levels, and a pressure that is also physiologically relevant. Aplasia and our benchtop model differ in that Aplasia has 20 pulmonary arteries and our model only has 2 pulmonary arteries. We need to figure out how to establish a connection and determine a way to relate these 2 results. Our software and benchtop model both also fall short of the clinical diameter estimation of 3 to 4 millimeters, which is indicated by our sponsors. We'd like to thank our sponsors, Dr. Vetticuttle and Bennett Samuels from Helen DeVos Children's Hospital, our MTU biomedical advisors, Dr. Rao and Dr. Goldman, and our Aplasia advisor, Dr. Broom.